All right, good morning. Okay, so once again, I pulled up the final exam information. It's Tuesday, December 13, 1 p.m., 2-hour exam. It'll be in the same place as last time, same general seating location. Find out where you're supposed to go before you get there, just like the previous times. I think we've decided that the final exam will have 20 questions. Okay, 20 questions. Each one will be worth 10 points. So the final exams out of 200 points. And I'll tell you more about it once we have the whole thing finalized, which should happen by tomorrow. All right, so for those of you that responded, that took the survey, thank you very much. I got some very useful information. This is the result as of this morning, about 10 minutes ago. We've got good stuff here. So this tells me which ones to start. And I'm just going to go in order of popularity. Okay? Now this survey will remain open for the rest of the week. And if you want to change your mind, or you can take this multiple times. So as things go on, if you want to change your opinion, feel free to update your response. If you have not responded, please do so. I need the information to tell me what you want to see. Okay, so survey says the most popular one as of now is number 10. Number 10 deals with the level curve. Question says the level curve of this function of 3 variables, z minus x squared minus y squared, that passes through the point 1, 2, negative 3, intersects the xz plane along the curve, and you have 5 choices here to choose from. Essentially, we got to figure out what it looks like when this thing intersects the xz plane. Keywords here are the level curve. Okay, when you have a function, level curve implies that you want the dependent variable to be a constant. So here we want f of x, y, z to be some constant k. So we went from a 4-dimensional thing to a 3-dimensional. So this is a level surface, Same idea as a level curve. A level curve is a 3-dimensional thing that we take a slice. This is a 4-dimensional thing that we take a kind of a slice and we get a surface. Now the value of this constant, of course, depends on the point that this thing intersects. So here we're seeing that k, whatever this k is equal to z minus x squared minus y squared. And this thing has to pass through 1, 2, minus 3. So that's going to tell you what the value of k is on this level surface. If you plug it into here, we get negative 3 minus 1 minus 4. So that's negative 8. So therefore, we see that z minus x squared minus y squared is equal to negative 8 on the level surface at all times. Now you know what it looks like. You know everything about it. We'll figure out what happens on the xz plane. On the xz plane, y is equal to 0. So if I go back to here, right now it's a surface, but the surface on the xz plane is going to turn into a curve. So this thing reduces to z minus x squared is equal to negative 8, or z is equal to x squared minus 8. Make sense? Okay, so that's a level curve, level surface, level anything. It just means that the dependent variable is a constant. Okay, next one according to the survey is number 15. Number 15 says that assuming that the equation xy squared plus 3z equal to cosine of z squared defines z implicitly as a function of x and y. We want to find the partial derivative of z with respect to x. Okay, so this means that z is a function of x and y, but x and y, those two things have nothing to do with one another. They're completely independent of one another. Of each other. Okay, so to start, this is very simple. You simply take the partial derivative of this equation on both sides with respect to x. Okay, so here's on the left. On the right, we take the partial with respect to x of cosine of z squared. Now, I've got to remember that z is a function of x and y. Starting here, when you take the partial with respect to x, y squared is a constant. So this is no different from 2x, right? So derivative of 2x is 2, derivative of constant x is constant. So we get a y squared out of the first term. The second term here, that 3 is a constant. The partial derivative of z with respect to x, we don't know that. In fact, that's what we want to find. So it would remain unknown at this point. It's simply the partial of z with respect to x. On the right-hand side, same idea. Derivative of cosine of blah is minus sine of the same blah. And then the chain rule says take the derivative of blah, right? So multiply by derivative of z squared is 2z partial derivative of z with respect to x. Okay, so far so good? Okay, now we'll just move things around until we can find out what partial derivative of z with respect to x is. So let's see, let's bring this guy over and kick the y squared to the other side. Just doing algebra here, simple algebra. Let's factor out the partial z, partial x. And then finally divide by all that square in all the stuff in the brackets. We'll get partial derivative of z with respect to x is negative y squared divided by all of that. Okay, make sense? Good? Good. Okay, good. We're making good progress here. Next one, according to the survey, goes to 48, number 48. So kind of a jump here. Number 48, I'll write down the question here. Green's theorem yields the following formula for an area of a simple region R in terms of a line integral over the boundary C of R oriented counterclockwise. So remember what Green's theorem says. Okay, so that's what Green's theorem says, where F is the vector field, a two-dimensional vector field, and R is the boundary of the region D. So if that's D, then we normally orient this in the counterclockwise direction. So that's what Green's theorem says. Essentially, this question wants you to find out, there are 5 equations given here. We want to know which one would give us the area of the region. So the first one is negative c y dx. The line integral of y dx, line integral of x dx, 1/2 line integral y dx minus x dy, and then negative x dy. Okay. So if you look at Green's theorem here, if you want Green's theorem to give you the area, so that's what we want to see. If you do a double integral of dA, you get the area. So this implies that qx minus py must be equal to 1, right? So if you have qx minus py is equal to 1, whatever this vector field looks like, then it'll end up giving you the area of that region. So remember that the vector field is assumed to be pq, and then dr, in usual Green's theorem application, we assume that to be dx dy. So the line integral, usually in the most common Green's theorem expression, we get this kind of thing, p dx plus q dy. Okay, so here's the key thing here. Each of these is going to have a p. Each of these is going to have a q. I want to find the one that has qx minus py to be equal to 1. And that's the answer I want. Okay, so look at here. This p is the one attached to y, dx. So here p is equal to y, right? And q is equal to, well, 0. And by the way, notice it's minus 1 here. So we can actually say that p is negative y because of the negative 1. So we have to check, is qx minus py equal to 1? Yes, no? Well, qx is what? 0, right? Py is minus 1. So is 0 minus minus 1 equal to 1? Yes. So this guy here, according to Green's theorem, would give me the area. That's exactly what we want to see. So this is the one we want. Okay, if the first one wasn't the right one, then you just keep on going until you get the right one. So this is a question testing if you know the statement of Green's theorem. There's no vector field given, there's no R given. It's entirely just playing around with the formula of Green's theorem and see if you could get some kind of a feel of what this thing is doing and what we want it to do. Okay? Good? All right. So that's 40A. Let me mark this down. Next one, according to the survey, is, we're back to number 20, no, I'm sorry, 18, number 18. Number 18 says, for the function f of xy is equal to x squared y, find the unit vector u for which the directional derivative is 0. Directional derivative at the point 2, 3 is 0. Okay, so what's the formula for directional derivative at any point xy for now? It's got something to do with the gradient. Yeah. That's right. Yep. You got to find the gradient of that function. Very good. Xy dotted with some unit vector, u. Okay, so if you want this to be 0, and that comes out of the dot product of two vectors, that's a vector, that's a vector. The only way this can be true is if the gradient is perpendicular to that unit vector, right? So this says the gradient of f at 2, 3 here, we just do 2, 3, is perpendicular to the unit vector. So let's find out the gradient at 2, 3, and then we're given 5 vectors here. We have to find one that's a unit vector such that when we dot it, we get 0. Make sense? All right, let's find the gradient. Okay, gradient is fx in the I component and fy in the j component. So fx is 2xy, fy is x squared, right? And at the point 2, 3, we get 12, 4. And we're given 5 choices here. The first one says u is I plus 3j. Second one is I plus 3j over root 10. C is I minus 3j. D is I minus 3j over root 10. And E is 3I minus J over root 10. Okay, let's look at them. What's wrong with A? It's not a unit vector, right? That can't be it. So that means C is out too, right? C is not a unit vector. That can't be it. How about B? That is a unit vector. But if I dot B, the vector B with a gradient, do I get 0? No, right? So that can't be it. Dot product, not 0. How about D? Does D look good? Yeah, if I dot these things, I get 12 minus 12, 0. And that is a unit vector. So this is good. Is a unit vector and dot product is 0. So that's perfect. So therefore, that means that as this function changes, if you go to this point, and you don't want this to change anymore, then you want to go in that direction, I minus 3j over root 10. Essentially, you're traveling along the level curve. That's what you're doing. And this one, for obvious reasons, is not going to be the right one. The dot product is not 0, even though it is a unit vector. All right, questions on this? Good? Good. Good, good, good. We're making good progress here. This is excellent. Okay, next one. Next one. Where's my paper? Next one, the survey says we're looking at number 31. Aha. The area of one leaf of the 3-leaved rows bounded by r is equal to 5 sine 3 theta is okay, so you might remember that if you have cosine or sine of some number times theta, if the number is odd, that's how many leaves you have. So here is a 3, so we have a 3-leaf rows. And then if it's even, then you have twice of that. Okay, so what we got to figure out here is what this thing looks like. And we want one leaf of this. So to graph this, it's actually not too hard. When theta is equal to 0, we know sine of theta is 0. So theta 0, r is equal to 0, right? When theta is equal to pi over 6, r is equal to sine of 3 pi over 6 is 1. So r is equal to 5. And this tells you that it reaches the maximum radius at theta is equal to pi over 6. This is theta is equal to pi over 6. So at this pi over 6, it goes to 5 units away from the origin. And between 0 and pi over 6, it's just going to form the lower half of that leaf, kind of like that. And theta r is going to be 0 again when theta is equal to pi over 3, right? The very next time r is going to come back to 0 is at pi over 3, which is twice of this. So what it's going to do is it's going to form the upper half of that and then come back to the 0 radius. So this is one leaf of that. We can find the area of any of those 3 leaves. They are symmetric. They're the same area. But we got one drawn here in the first quadrant, and it's the simplest one. Let's just work with that one. So notice what happens. We're going to start theta at 0, and we're going to end at pi over 3. We don't go beyond pi over 3, because pi over 3 is the very first time r comes back to 0. So that completes one leaf of that. And this is a circular kind of trig kind of thing. So we're going to use polar. We're going to integrate dA, right? And in polar, dA is r dr d theta. And what are the bounds of r? Good. 0 to 5 sine 3 theta, right? This is as far as you're allowed to go. So this says that we need to integrate r first because r depends on theta. So theta goes last. 0 pi over 3, 0, 5 sine, missing a 3, sorry. 5 sine 3 theta. We're integrating dA, that's r dr d theta. Okay, once you got this far, the rest of this is pretty straightforward. 0 to pi over 3, 1/2 r squared, 0 to that. So 1/2 times 25 sine squared of 3 theta d theta. (25/2) is a constant. And then I have sine squared of 3 theta. I need to use my identity. 1/2 minus 1/2 cosine of twice of 3 theta. So 6 theta. Okay. So 25/2, 1/2 theta. And then we're going to integrate this, and we get minus 1/12 sine of 6 theta, 0 pi over 3. Okay, looking at the sine of 6 theta here, at pi over 3, we get sine of 2 theta. That's a 0. That's 0, sine of 0 is 0. So this doesn't contribute anything. That's a 0. And here we just have 1/2 times pi over 3. So that's 25 pi over 12. All right, so that's the area of that one leaf of this rose thing. Okay, now the hardest part, the most tricky part of this question is the bounds of theta. Right, the bounds of r is obvious. The theta is a little bit less obvious. And you have to determine that using the shape of this thing, that leaf. You start when r is equal to 0. You find out when it gets to the maximum, when it comes back to 0 again, and that completes one leaf. You don't go beyond that bound. All right, are we good on this? Yes. Right. I don't know. Have you tried it? Try it and let me know. Well, no, sounds reasonable, right? But why don't you try it and let us know? That's right. Yeah. So oh, that's a good point. So therefore, if you do 0 to 2 pi, that wouldn't be right then, because you're counting part of these twice. That would be right. Yeah. But I don't, I think the easiest way is to figure out one leaf and then, or maybe even half a leaf and multiply by 2. So you could have done 0 to pi over 6 and multiply by 2. Yeah. Okay, I guess we answered your question then. Thanks. Other questions about this one? Okay, so we wrapped up 31. Let me see what my list says we're going to be doing. We're going to be jumping around to 52. We're given a vector field. F is xi plus yj plus zk, and sigma, that's just the a name for the shape, is a sphere of radius 1 with an outward normal. So it's a very normal. Get it? Yeah? Gee, tough. All right. So what are we looking for here? We're looking for the surface integral over that thing, f dot n ds. Okay? So we're looking for the surface integral of this vector field over the sphere of radius 1. By the way, this is also written as, if you remember, f dot ds. And because this is a closed surface, we have a very nice theorem we can use. We can find the triple integral of the divergence of dv, because we have a closed surface. So divergence theorem says, let me write that down. Right, that the integral of the divergence inside that thing is equal to the surface integral on the boundary surface. The boundary surface of a sphere, solid sphere of radius 1, is the surface of that sphere. So that's what we're trying to do. So you could do either way. You could just calculate the surface integral way. If you want to do it that way, that's fine. Or you could simply use divergence theorem. Taking a look at the vector here, the field is very simple. The divergence of this is a very simple number. So that's a clue that divergence theorem will be very useful here. Divergence, remember, is the partial with respect to x of the I component plus partial with respect to y of the j component plus partial with respect to z of the k component. And we get 1, 1, 1. We get a 3. And we're just integrating over a sphere. So that's also a very easy thing to handle. Okay, so this becomes a constant as opposed, we don't even have to find the normal and all that stuff, which is what you would have to do if you were doing the surface integral. Okay, so it seems very simple, right? We're doing dealing with a sphere, so we're going to do spherical. Go into spherical here. The entire sphere, so we want phi theta to go 0 to 2 pi, as usual. What about phi? If you want the entire sphere, what do you want phi to go from? 0 to, very good, pi. How about rho? 0 to 1, yeah? We want the entire sphere of radius 1. So what we're doing here, we're doing 0 to 2 pi, 0 to pi, 0 to 1. Divergence of the field is 3. And what's dv in spherical? What's dv in spherical? Rho squared. What else? Sine phi. Okay, and the order of integration, d rho, d phi, d theta, right? In this problem here, is the order of integration a big deal? No, they're all constants, right? You can go in any order. Doesn't matter. So, and this looks like a very simple one to do. 0 to 2 pi, 0 to pi. First round is with respect to rho. So we get rho cubed, 0, 1. And what did I do here? Pi, right? So that's a 1. Integrating sine, we get negative cosine 0 to pi. And this will give you negative, negative 1, minus, minus 1. So 2. And then here will just be a theta, 0 to 2 pi, so 4 pi. Okay? All right, so here's a good problem where divergence theorem is really, really nice, really useful. 52, let me check it off. Good. Questions? Good? Okay, good. All right, next one. Survey says, number 51. Vector field is cosine of zi plus sine of zj plus xyk. Sigma is the complete boundary of the rectangular solid region bounded by the planes. Let me write that down. and n is the outward uninormal, as usual. Okay, so what are we dealing with here? We're dealing with some kind of rectangular solid. X goes from 0 to 1, y goes from 0 to 1, z goes from 0 to pi over 2. So we get this box, like that, completely bounded. So it's a closed surface. And once again, a divergence theorem application here is worth considering. We want n to point out. Okay, so you count the number of faces that you would have to deal with if you were doing a surface integral. And we have 6 faces. Each one is pretty simple, so it's not a really that big a deal, but it's 6 surfaces nonetheless. If we go to the divergence using divergence theorem, then this involves one triple integration over a box. It doesn't take a whole lot of effort to decide which one is easier to deal with. 6 faces or one triple integral over a rectangular box. That sounds like the one we want to deal with. So let's start by finding divergence. And what's the divergence here? 0, right? Because we want a partial with respect to x of the I component. There's no x in here, that's a 0. Partial with respect to y of the j component. There's no y here, that's a 0. Partial with respect to z of the k component. There's no z here, this is a 0. So I'm integrating a 0, and therefore I get a 0, right? Okay, that one wasn't so bad. Questions? I think we got time for at least one more, so let's keep going. Next one, according to the survey here, is number 50. This one would take a while, so that's probably the last one we can do today. So here's sigma, the surface. It's a paraboloid, and we stop it at z is equal to 4. So paraboloid with z equal to 4 and below. N is an upward normal. The vector field is xi plus yj plus zk. So that thing grows up, and we stop it at 4. And at 4, this is x squared plus y squared is equal to 4. The projection of that will be a circle of radius 2. Okay? And the normal is going to be pointing upward. So we're looking at this surface, and the normal is actually going to be inside. And that's the only way it can be pointing upward. Okay, for this one here, we're going to have to do the usual surface integral way. Because we don't have a closed surface. This thing is open, right? Divergence theorem is not going to tell us the right thing. And we have to make sure that this normal vector RU cross RV is pointing upward. Okay, let's parameterize our surface. You can do this various ways. I'm going to just let x be u, and I'll let y be v, and z is just going to be u squared plus v squared. And the bounds of u and v, this is where we're going to be looking at the projection of the paraboloid onto the xy plane, circle of radius 2. So this is just describing a circle of radius 2 on the x and y plane. RU and RV are not hard to find. And crossing them, we don't know, usually you can't tell which order you want to cross. You just cross them and then make sure it's pointing in the right direction. If you do RU cross RV, we should end up getting minus 2U, minus 2V, and 1. And a positive Z means it's upward. So that's good. We got the right direction here. Okay, now we're going to go back to the vector field here, xi, yj plus zk. We're going to replace xyz with the xyz components of the surface. So x is u, y is v, z is u squared plus v squared. Then you do that. Okay, then we're running out of time. I'll finish this before I post the notes. So what next thing you do is you do this, and then you're going to go to the polar coordinates to finish the integration. So there's a little bit left here. Probably we could have done this a little bit smarter and just parameterize this in polar to start with. Probably should have done that. But anyway, this is also fine. Next, then you change to polar and integrate. Okay, so Wednesday and Friday, we'll just continue doing this stuff here. We've covered a lot of things already. So make sure you fill out that survey. Let me know which ones you want to look at, and I'll do whatever you want me to do. See you Wednesday.
paraboloid. It's a surface.
It is. It's not a closed surface. There's an opening at the top, right? So if you think about a sphere, that's closed, so we can use divergence theorem. But this has the top open. That's right, but it doesn't say that it includes a circle that closes all the surfaces. How can it say that? It's not in the statement, so we don't repeat that. So it's an open thing. You can't repeat it.
Right here, when you did dot product, you said 1 times 12 minus 3 times 4. Why wouldn't it be 1 over root 10 minus 3 over root 10? Because that would be 0.
Sure, that would be 0. This is just changing the, okay, without this, it's still the dot product would be 0, right?
Right.
So this just divides whatever you get out of dot product by 10. If it's 0 to begin with, then it's still 0 after you divide by 10.
Why wouldn't it be 12 times 1 over root 10?
That would be, sure,
Oh,
but
okay.
minus 12 over root 10,
Right.
that's 0.
On 48, it was the
Okay, yeah.
How did you know that py equals 1?
Because I look at this thing here. P is the part that's attached to dx, right?
Yeah.
So this guy has a p equal to minus y.
Okay.
So py is minus 1. There's no q, qx is 0, and qx minus py is 1, and that's what I want to see.
Could you just explain that one more time? I'm sorry. I'm
Which
not.
part?
Just so you're taking.
Okay, p is whatever's attached to dx.
Right, I
So it's
understand
minus
that.
y.
Okay.
There's no dy here, so q is 0.
Oh. I see.
And then I took
You
partials and I subtracted them, and I get a 1.
Oh, you just take the